Good morning, welcome to National Science Week. My name's Jeremy Kruger and I'm the Project Director for the Tunnel Stations and Development Package on the Cross River Rail project. Today I'm proud to present to you an introduction to tunnelling on the Cross River Rail project. And in particular I'm going to talk through some of the design, some of the construction challenges and other methods that we're going to use to build the tunnels on Cross River Rail. Pleased to also be here in partnership with the Queensland Museum and the Queensland Government. So firstly, what is the Cross River Rail project? So a bit of an overview. It's a new 10.2 kilometre north-south rail line running from Dutton Park in the south all the way through to Exhibition Station in the north of Brisbane. Underneath the river we've got a 5.9 kilometre twin tunnel and there'll be 4 new underground stations, one in the south at Boggo Road, a new one at Woolloongabba next to the famous Gabba cricket ground, station at Albert Street in the middle of the CBD, and a new underground station beneath the existing Roma Street station. Also, as part of Cross River Rail, we're upgrading 8 existing surface stations, Exhibition in the north, and then in the south we've got Dutton Park and Fairfield through to Salisbury, which are all getting upgraded as part of the project as well. Finally, we have a new signalling system. It's called the ETCS, which stands for the European Train Control System. And that's a new signalling system that we rolled out to enable the trains to run faster and more efficiently and safely through the Cross River Rail infrastructure. Okay, so having a look at the actual tunnel, I'm going to focus on the tunnelling today, and you can see there a bit of a long section of the cross section through Cross River Rail. Starting at Boggo Road, the tunnel then dives down. The Boggo Road station is our shallowest station, it's about 14 metres. We then get down to Woolloongabba at 24 before we then head right down underneath the Brisbane River. At the maximum depth there, we're about 41 metres below the riverbed. We then start to rise back up into Albert Street at about 33 metres, which is our deepest station. We're staying quite deep in Albert Street to avoid the basements and other obstructions in the CBD. Continuing on to Roma Street before we then head back to the surface, joining the surface in the corridor next to the inner city bypass for those that know Brisbane, before we finish off at Exhibition Station. So that's a bit of an overview of the length of tunnelling and what the long section looks like. But how do we go about choosing this alignment? How do we go about designing this tunnel? And I'll step you through now how we prepare to embark on a massive infrastructure project like this. So first up, we do the GTech investigation. We need to know what rock we're going through. We need to understand the ground conditions so that we can actually design the alignment, design the tunnel, and work out what depth we need to take the tunnel through. There's always a bit of a balancing act between staying deep enough in the rock, so we'll get good quality rock, but also shallow enough so that the stations are at a high level so you don't have to go down many banks of escalators to get down to the actual platform. So it's a bit of a balancing act that the designers do to design the alignment. On Cross River Rail, you can see there on the image there, we drilled about 200 boreholes across the length of the project. That explored the alignment, the rock conditions. You can see a number of holes that were drilled in the river there to find the ideal location where we crossed the river and to make sure that we had good rock cover at that deepest point of the project. This drilling provides the information that really helps us lockway the design and gives us information on all the rock types that we found. You can see there an image in Albert Street where we did a lot of our drilling at night so as not to disrupt traffic and the pedestrians in the CBD. So on the back of the drill rig we core down and we retrieve samples from up to 60 metres below the ground. Those samples are called rock core and they're placed into trays. And you can see there on the right hand side of the image there how those cores are then used by the geologists and the tunnel designers to understand the strength of the rock. Is it fractured, is it solid, and how's it going to hold up the tunnel design? So the rocks that we found when we drilled for Cross River Rail, one of the main types of rock was the Neroli Fernvale beds. That's a grey type rock that you can see there on the image. That's the rock that predominantly the Brisbane CBD is built on. So if we look at the CBD in Brisbane, all the high rises and skyscrapers in the CBD, they're all founded on that Neroli Fernvale rock. And that's pretty much north of the river all the way through to our northern portal has that type of rock. As we head south under the river, the Kangaroo Point Cliffs, the famous Kangaroo Point Cliffs in Brisbane, they're actually out of a rock called the Brisbane Tuff, which is a volcanic from an old volcanic explosion in Brisbane many years ago. And that Brisbane Tuff is a very hard. It can be up to 5 times the strength of concrete, up to nearly 200 MPa rock. That rock exists all the way south of the river through our Woolloongabba site. Below the Tuff, we do have various bits of Nerali Fernvale, but then we also have what's known as the Aspley-Tingalpa Formation, which that type of rock is a sedimentary rock, so like a sandstone, mudstone type rock. So they're the 3 main rock types that we're going to tunnel through on the Cross River Rail project. And we're fortunate in that on our tunnel, all the way from Boggo Road, all the way through to Exhibition, we're in rock the whole way. So we don't have to tunnel through soft ground such as clay and sands, which can be a little bit more challenging. So it's quite fortunate on the Cross River Rail project. So that there gives a bit of an example of what the designers then do once they have all of that geotech information. They map out a long section to show the rock types, and that then enables the tunnel designers to get the right depth, the right alignment. You can see that big green there is the Kangaroo Point Cliffs tuff that I spoke of, and the purple after we go underneath the river, representing all of the Nerali Fernvale rock to the north. Just while we're on that slide, as we go underneath the river, there's obviously always challenges there. The yellow underneath the river there is all the muds and silts within the river. So an important consideration was to make sure that we were deep enough to avoid those silts and muds and actually be down in good competent rock as we go beneath the Brisbane River. And I'll talk a little bit more about that in a couple more slides. So that's the first thing that we do is we understand the geology and the geotech that we're going through. After that, we start the design. Now, on Cross River Rail, we've implemented what we call Project DNA. Now, Project DNA it's a digital twin. It's a virtual twin, if you like, of the tunnel, where we're actually designing the entire tunnel and the stations in 3D in CAD before we actually build it. So we create a BIM model, and that BIM model is used by the designers to spatially fit the design of the tunnel, work out how all the different rooms and everything come together. We also use other techniques such as GIS. You can see in the top right there, GIS, to locate spatially where the station fits in relation to other infrastructure, houses, roads, and everything else. Finally, one of the other techniques we've used has been a visualization model. This is actually it's a gaming technology, so it's the same technology that you use for your gaming. And what you can do, as you can see there, is you can create a virtual reality experience where you can actually sit in the model. If you come down to our experience centre down on Elizabeth Street in the Brisbane CBD, you can actually come and experience the virtual reality and see the computer model as it's generated. So what all of these technologies do, the BIM model, the GIS and the Viz, it actually enables us to visualise and create digitally what we want to then go out and build. We can do things such as clash detection to make sure we're not hitting existing building piles or utilities like power cables and stormwater drains, and do all of that testing first before we actually go out on site. So it's a way to make the construction both more efficient and safer. So this is the video that you can see in our visitor centre, and it shows an example of how we can use the visualisation techniques to actually take a train driver through what the tunnels. So this can actually be used to train operators and get other people familiar with what the new stations are going to look like and how you would drive through them in the new train. We also have these also for people walking through the stations, how the escalators and everything else, but I think Keith Allen's going to walk you through a little bit more about how BIM and architecture work this afternoon, so make sure you tune back for that this afternoon. Okay, so back onto the tunnel and the tunnel design. So once we've got our BIM models, you can see there an example of what the stations look like in terms of comparing it to the rest of the CBD. So In front of you there is our BIM model for the Albert Street station, just outside me here actually in the CBD. We have the station entrance, which is the large block on the left of the screen, and we have a second northern entrance. And joining those is the underground cavern. So that underground cavern is what we're currently focused on mining out, and that will become the platform for the future rail station when it is built. Joining either end of those caverns is twin tubes that you can see, and those tubes are what we call the running tunnels. So they'll carry the trains between each of the stations. Those running tunnels will be mined out through TBM, and the main caverns will be by roadheader. And I'll go into a little bit more detail on each of those different tunnelling techniques. So when we look at the main running tunnel, that tunnel design is typically circular. It's circular because of the nature of the TBM excavation technique that we use. It's also, from a design perspective, it's very structurally robust to have a circular section. Now, when we're designing a tunnel, one of the first things we need to do is make sure that the trains fit. So we go through what we call as a space proofing exercise, where we make sure that the tunnel is big enough to fit the train. You can see in the middle of that diagram there, the train. And what we also look at is what we call the kinematic envelope. So we look at when the train's actually moving, it's on suspension, it will move around. We need to make sure that there's enough room in there for the train to have its natural dynamic kinematic movement. Other features that we need to fit into the tunnel, up the top we've got the pantograph and the overhead power that feeds the electricity to the train. Obviously we've got the tracks underneath on a track slab and the rails that the train runs on. We also provision on the right hand side, you can see a walkway there. So when we're designing the tunnel, we need to make sure we've got provision for maintenance walkway, but also emergency egress. And then finally, there's a number of cable trays there. So we run emergency power, lighting, we have dewatering sumps, and other cable trays for signalling and fire hydrants and things like that. So very important process to get that space proofing right, and once that's locked down, we can then lock down the size of the tunnel and define the diameter that we need for the TBM. In this case, our overall diameter is about 7.2 metres, or internal it's about 6.4. Okay, so that's how we do the running tunnels for the TBM. When we look at the design for the caverns, these are slightly different. It's not circular, it's more of a traditional arch shape. And in fact, it's that arch shape that helps the tunnel support itself. If you actually think back to old Roman arches, where they were all in compression holding up together, the same technique is really used to hold up a cavern. So what you can see around the edge of that arch is a series of rock bolts, and they're drilled into the rock to support the rock and stitch the rock together. We then have a thin lining of shotcrete lining that helps pin together the face of the rock and prevent any of those smaller blocks. But really all we're trying to do here is we're trying to get the rock to do all the work, and by pinning the rock all together, it'll form a natural arch and enable you to open up and form that cavern. When we're excavating the cavern, because of the side of it, we typically do it in what we call a heading and a bench. The heading is done with a road header in two halves there, you can see, and then we come back and take the bench out in a slightly larger excavation. Overall, that creates it's about a 20 odd metre wide span there, and you can see there the two TBMs that will then come through the cavern, connect the running tunnels. Finally, once we've got all that shotcrete in place, we then put a primary concrete lining, which is just a thick, up to 600 millimetre thick, lining of shotcrete, and that'll be the final lining for the cavern. Okay, so tunnelling under the river. Now, people always ask me, how do you go under the river? How do you stop it leaking? And they're all really good questions. Fortunately, this isn't the first tunnel that's been done underneath the Brisbane River. A few years ago, we had back in, I think it was about 2009, we had the Clem 7 tunnel, which is just around the corner from here underneath the Story Bridge there, which was a similar TBM tunnel for the Clem 7 motorway. That also went under the river. So we were able to both learn from what they've done on that project in terms of how they tunnelled underneath the river, but also apply some of our own investigation there. So some of the key points that we look for is to make sure that we're tunnelling down in the actual rock and not through the mud and silts and alluvium. Being in that rock gives you a little bit, gives you better structure around the tunnel so that you have a good structure. We also have the provision as we're tunnelling under there to do grouting. So if that rock is fractured or there's a potential to get a crack or a fracture that could leak into the tunnel, we're able to grout that up to stop water leaking into the tunnel. And finally, the segments that we use, the segments themselves are actually got a gasket between them. So as we're building the segments for the tunnel underneath, those segments are compressed together with a gasket in between, and that gasket also stops the infiltration of water. So there's a number of methods we use there, both location, waterproofing gaskets, and grouting that will help to address those challenges as we're tunnelling underneath the Brisbane River. As I mentioned earlier, we're about 41 metres deep from the river surface when we tunnel under, and that gives us about 8 or 9 metres of good rock cover as we go beneath the riverbed. Now, one of the other interesting challenges we have on across River Rail is flooding. Now, our CBD station at Albert Street there is in one of the lower parts of the Brisbane CBD. It's also a part of the CBD that's historically had some big challenges. You can see the images there from 1974, the flooding there with Festival Hall, which is immediately adjacent to the Albert Street station. And then even in 2011, just a few years ago, that there's the corner of Mary and Albert Street. Mary and Albert Street, right where our station is. You can see there the Brisbane River has flooded up as well. So when we're designing our tunnel, this is a key consideration for our project. It was how we manage that. Now, during construction, we're employing methods using temporary floodgates and protections. So you can see there on the right-hand side an example of where you could have temporary measures there to prevent flooding. That one was actually on another project I worked on, Airport Link. But on the left-hand side there, we've recently completed the temporary flood wall around Albert Street Station. You can see that there, the concrete wall with some blue panel gaps in it. That's how we're going to manage flood, if a flood should occur during construction. That's how we'll manage to keep flood water out, because obviously once it gets in the tunnel, it will fill the whole tunnel, and that's something we definitely don't want. So they're the types of measures that we use during construction to keep floodwaters out. In the permanent design of the tunnel, over the escalator shafts, they'll have effectively a panel that comes down to seal that, and that will provide the long-term mitigation for flooding at the Albert Street station. Okay, going to move on now to construction of the Cross River Rail tunnels. And spend a little bit of time here about the two different types of techniques, how we set up a construction tunnelling site, and then I've got some great video clips as well from some other projects to show you what the tunnelling looks like. So firstly, for the Cross River Rail project, we've set up a site at Woolloongabba, which will be our main tunnel launching site. From Woolloongabba, we're going to have 2 tunnel boring machines, and they're going to be launched north, continuing underneath the river through Albert Street, and then daylighting up at the near Victoria Park, next to the inner city bypass there at the northern portal. And that'll be similar to that image there of the TBM you can see in the top right-hand corner. From Woolloongabba heading south, it's a much shorter distance there. It's only just under a kilometre to get to the Boggo Road station. So heading south, we're going to use a different type of tunnelling technique, which is road headers, and you can see there the image. The road headers also get used for the caverns. So road headers, given the nature, are very good for non-circular tunnel profiles. They can cut to arches, larger profiles, whereas the tunnel boring machines have a set diameter circular tunnel profile. In terms of length, the road head is heading south. As I said, it's about 950 metres. Heading north, we've probably got about 4 kilometres of TBM tunnelling. Add in the caverns there, it's just under 5 kilometres of tunnelling to the north. Okay, so to get ready for our tunnelling site, over at Woolloongabba there, one of the first things we do is plan the layout of the site. Now we're quite fortunate at our Wollongabba site. It's about a 4-hectare site, so it gives us lots of space to set out the different support functions we need there. So we plan that first in our BIM model, and what you can see there is the tunnel spoil shed on the right hand side. You can see a large ramp in the middle with piles either side. That'll be a long decline ramp so that trucks can drive down into the box. At the top of the screen is the main station box where the station will be built, but also where the TBMs and the road headers will be launched from. And then across the site we have other water treatment plants. We have a maintenance shed for doing a workshop for doing maintenance on the machines. And we also have storage shed, HV transformers. We have ventilation equipment. There's quite a lot of support activities required. And that image there just shows a bit of a layout there. This was just taken last week at our Wollongabba site. So for those that might have driven past the site, you can't see what's over the hoarding. That's behind the hoarding there. We've got a very large excavation there. That's the main station. Heading off to the left of the screen will be the TBMs heading into underneath the river into the CBD, and heading south underneath the busway there beneath Stanley Street will be the road header excavation heading down to Boggo Road. So you can see they're starting to have, there's a detention basin, there's side office sheds on the left hand side, and other support works all getting ready for tunnelling. Now Wollongabba, that's a really big site. At Albert Street, we've got the other scenario where we're a very small, very crammed site. So again, we've used the BIM to help plan and set out for the site. Because of the constrained site that we have at Albert Street, what we're doing is we're sinking a shaft, and it's from that shaft that we'll commence our road header excavation. On the left-hand side of that image is the main station box. That will just be an excavation in which the station, with all the escalators, the VT. But on the right-hand side, we've poured a slab there and put a shed on top. And you can see coming down there the shaft and then the 2 adits that will go into the tunnel to create the cavern there. So on that site is a large acoustic shed. We build acoustic sheds there to keep the noise, the dust, the vibration from disrupting nearby residents. There's a lot of hotels and residential towers near to our Albert Street site. So it's very important that we take into consideration their requirements and needs and build an acoustic shed. So within that shed, we've got that shaft, that circular shaft that you can see in the middle. That big white box on the left-hand side is one of our ventilation dust scrubbers. So when we get dust and everything in the air, that helps to scrub and clean the air before it's discharged out of the shed. And you can see the green gantry crane running above the top. So that's used to lower equipment down into the shaft and also remove the spoil and the muck. So at our Albert Street shaft, for those that have been in the CBD or live nearby, you will have maybe got some of the SMSs and heard about the blasting we've been doing there. So that blasting has been to get us down deep enough and create these adits to create enough space so that we can then take the road header machine down there. The road headers are very large, they're 22 metres long, so we actually got to do a bit of traditional old drill and blast tunnelling excavation before we get down there. So on the left-hand side there is a typical blast pattern. You drill horizontal holes into the face. Those holes are then charged with explosives. You can see there an example of it's a photo of a rig that would drill those holes horizontally into the face. Once those are then charged with explosives, we clear the shaft, we clear the shed, and then the shot fire will come in, siren will sound, and then we'll detonate the blast. The blast, it sounds like rumbling thunder. It'll only last a few seconds. You'll feel a little bit of vibration and a rumbling thunder type sound. And then after the blast, this is what you see. So what we're aiming to do here is to fracture all of the rock in that face. We're looking for good fragmentation of that rock so we can then just come and muck that out with an excavator. On the left-hand side, you can see what are rubber blast mats. So they're hung down in front of the face to try and control fly rock and other air pressure blast. And then the shot fire will come down and inspect and make sure that all the explosives have detonated. So what we do is we load the face, we detonate it, we remove the soil, remove the rock, the fragmented rock, come back in, put support, bolts and shotcrete, and then repeat. So we adopt that cycle for drill and blast tunnelling. Okay, so the other main bit of tunnelling we're doing at the Albert Street site, and this is also occurring at our Roma Street site and also Woolloongabba, is using road header tunnelling. So road headers, you can see there in the machine there, are up to 22, 25 metres long. They weigh over 115 tonnes, so that's over 50 or 60 normal passenger cars that we would have. So they're very large machines, very heavy machines. We've got 5 Mitsui S300 road headers used on Cross River Rail across our sites at the moment. And what they have is on the right hand side, they have what we call a pineapple. That's a cutter head that is rotated. I've got a great video that shows how that works shortly. They use that to grind away and cut the rock. It's got a series of metal picks on the cutter head that help grind away that rock. That rock falls down to the front of the road header, is taken through a conveyor and then out the back of the conveyor and loaded either into skips taken to the surface through those cranes, or for our Woolloongabba site, we're actually able to drive one of our 6-wheel Moxie trucks down and load directly into the back of it. So that there is an image of the 2 road headers that we recently commissioned for our Woolloongabba site. So it gives you a bit of a scale of the size of them with the workforce there, the proud workforce for those 2 road headers, and they'll be doing the majority of the tunnelling for the caverns at Woolloongabba and then the 2 drives down to Boggo Road. And as I mentioned, this is how that's spoiled. So once we cut the face, the spoil comes out the back of the road header, and we then either load that into skips or into trucks and then cart that back to the surface for spoil handling, and ultimately it'll be transferred into a truck that we would then take to one of our spoil disposal sites. The spoil disposal sites we're using on Cross River Rail, we've got a number to choose from. There is a development site down at Larapinta. There's a quarry, Pine Mountain, out at Swanbank. We're also backfilling old quarries. And some of it's also going out to the Trade Coast area out near Brisbane Airport as fill for development. Okay, so with those road headers, the actual tunnelling method is to cut the face, as you can see there. Typically we would advance about 1.5 to 3 metres a day. So the process, it's very much a repetitive process. So we cut the face, we then come in and we bolt, and we install those bolts that you saw in the diagram earlier. We bolt up to support the rock, and then we put a layer of shotcrete. And once we've got that first layer of shotcrete, we can then allow that to cure, and then we could go for our next advance. And it's just that repetitive process of cut, bolt, shotcrete, and then repeat. And then sometimes there's building up thicker lining of shotcrete depending on what the rock strength is and what the tunnel design is. Okay, so we've got a great little bit of a time lapse and video here. This is our shaft at Roma Street. So we've excavated that shaft down, and now what you can see is lowering down the parts of that road header down into the shaft and then assembling. So that's the front apron going on, and then the cutter. As I said, overall the road head is about 115 tonnes. Once the road head is all assembled underneath, we can then start the cutting and excavation. So the cutter head will rotate, and then the operator will carve out against the rock the tunnel profile that they want to cut and commence the excavation. So as you can see there, that boom's moved back and forth to cut the profile. The rock drops down on the front into that apron, and then that can be then conveyed out the back Any of that dust that is caused as we are doing that cutting exercise is sucked back up through our ventilation system, put through the scrubber so that any air that finally exhausts outside of those sheds is all being cleaned and has all particles removed to ensure the safety of the community, but also the workers as well. Okay, so that's how we excavate the road header tunnel. Once we've excavated the tunnel profile, we then need to come through and cast the final cavern lining. So typically that's done using an arch form. So it's a very large concrete shutter, concrete form. And you can see on the outside there the fresh concrete in the foreground that's been poured. So we set that arch up, we fill that with concrete to create the final lining, and then we just keep stepping that arch form through the cavern. So we're not up to this stage yet on Cross River Rail. That's a photo from another project, but that'll be the last stage when we're doing the excavation for road header tunnels. Okay, I'm going to move on now to TBM tunnelling. So the tunnel boring machines on Cross River Rail will have two of these. They're 7.2 metre diameter, and each of the TBMs is over 165 metres long. So that's longer than two Boeing 747s, or it's as long as a little bit longer actually than the 6-car trains that we currently use on the Queensland Rail network. So very large piece of machinery equipment. In fact, the weight of the TBMs there, nearly 1,500 tonnes. That's as heavy as 6 full trains. So it's a very large piece of equipment. As I said, the cutter head's 7.2 metre diameter. It's made up of 39 cutter discs. It's those discs that actually do the cutting work as the TBM advance. And the TBM runs 24/7. So 24/7 that'll operate, a crew of about 15 to operate a TBM. And that'll run 24/7 once it's launched from Woolloongabba. It'll take just under a year to make its journey from Woolloongabba all the way up to the northern portal. So you can see there a bit of an image of the front face of a TBM when it's cutting. That cutter head's a little bit different to the ones we'll be using, but it does give you, I guess, a bit of an illustration of the scale and the size of these machines. Okay, so to create a TBM tunnel, first we need segments. So you can see there's a photo of each of these individual concrete segments that is cast, and those segments are put together by the tunnel boring machine to create a ring, and it's those rings that create the final lining for the tunnel. As the TBM advances, it installs those rings, and that's how we create the TBM tunnel. Now each of those segments weighs about 4.2 tonnes, so they're very heavy, and it takes 6 segments to make up each individual ring. The segments themselves are about 1,700 millimetres long, so every advance or every ring that we install gets us about 1.7 metres of tunnel constructed. The TBM's basically like a big factory. We feed it full of segments, it installs those segments, cuts the face, we take the spoil out, and it's a sausage machine that just keeps going, and we can get up to 20 metres per day with the construction of the TBM. So with those segments, when we assemble them in the ring, that's what they look like. This is a recent shot from the precast factory out at Wacol, where we've recently done the trial segments for the ring and assembled them to show how they go together. So if you can imagine the machine as it's driving along, it will be installing each of these rings progressively as it advances. So good progress. Those segments will now be constructed over the next 6 to 12 months out at Wacol there, and then we'll have them delivered in sets of 6 ready to produce those rings over the coming year. We're looking to have those TBMs launched from Woolloongabba hopefully early in 2021. When we assemble those rings, they're held together by steel dowels temporarily, and then we grout around the outside so we get a strong connection between that ring and the surrounding ground to carry all the loads and provide the final structural lining for the TBM tunnel. And from the inside, that's what a finished tunnel looks like. I think this might have been from Sydney Metro, which is appropriate because the TBMs that we're using on Cross River Rail are actually Herring Connect machines that we use for the Sydney Metro. Those machines have been brought up to Queensland. We're doing some refurbishment out at Pinkenba. Oh, sorry, I'll just go back there. Refurbishment of those machines out at Pinkenba, with the heads out at the main cutter head being refurbished in China. But that's an indication of what the inner lining of the TBM tunnel once it advances and we've installed those rings. As I said, up to 20 metres a day is the advance rate, so quite good production can be achieved with TBM tunnelling. And all of that can be done with millimetre precision. So we use a laser sight down the centre of the tunnel that inside the TBM, the operator can control the direction of the TBM, and with the modern technology and laser capabilities, we can get millimetre precision on the final location of where that tunnel goes. Okay, so the next slide I wanted to show you is this is actually a time lapse from the airport link where they also had a TBM. What's interesting about this time lapse is you can actually see the TBM as it's advanced through the cavern. Now this will be a similar process that we use. So our TBM will be launched from Woolloongabba and then advance through the caverns we built at Elgin Roma. And you can just see how long that TBM is as it advances. So on that whole backup gantry, which is up to 165 metres long, you can see the cutter head. I'll just go back and replay that. So you can see the cutter head at the front. Immediately behind the cutter head is the shield, which provides the jacking rams that advance the head. Immediately behind that shield, we have what we call the erector ring. So that's a vacuum that installs the actual segments. And then there's a bunch of conveyors, there's HV transformers, there's control cabins for the operator, for the driver. We also have crib rooms and a safety refuge for the operators. So while they're down on that machine, they can work from inside of their factory for their shift and not have to come back to the surface. So really very advanced and great bit of technology. And they'll be used two of them on Cross River Rail to be used to do those tunnels north of Woolloongabba. Okay, so as I mentioned, the machine's currently being refurbished out at Pinkenba. So this was from just a couple of weeks ago when we were out on inspecting the progress there. And you can see that backup gantry that you saw that video. We've got that all laid out. They're going through refurbishing, making sure that the machines are all good and ready for construction. That cutter head will go on the face of that machine there. The cutter head's currently in China getting new bearings, new hydraulic rams and cutter head. It'll be shipped back probably later this year, and then they'll go through the final assembly before it's brought to Woolloongabba and dropped into the shaft, ready to commence tunnelling early next year. And finally, just finish with another image. This one's also from our friends down at the Sydney Metro project, just showing when that TBM does arrive, reaches its final breakthrough. So you can see there the TBM pushing, advancing forward. You can see each of those individual discs at the front there. Each of those disc cutters weighs hundreds of kilos. They're very heavy, but if you want to come and have a look at one, we've actually got one here in our visitors centre. I think you'll be amazed at the size of them, and they do all the heavy lifting. They do all the cutting of the rock as we're going to advance through the very strong Toof and Nerily Fernvale rocks that I spoke to earlier. Okay, so that's how we finished the twin tube tunnels. You can see the final tunnels there as they're going to be constructed and excavated and lined. One of the other tunnelling activities we then embark upon is excavating the cross passages. So we've got 16 cross passages on our project, and the cross passages are very important because they're part of the safety function. So if we ever have a breakdown or a fire in one of the tunnels, this is where you can safely egress from one tunnel into the other tunnel and remain safe. The cross passages are also used to house Mech Elect equipment that's required to service the tunnel and keep the tunnel operating. So to construct these cross passages, what we need to do is we actually need to come back in and cut out and remove some of those segments that we installed. And you can see there in that image, and that one's from a Legacy Way project here in Brisbane. When you cut out and take away that segment, you can see the rock behind it that the TBM machine's gone through. We then use a small hydraulic excavator or hammering rig to excavate out that material through the cross passage, shotcrete that up and bolt it, similar to what we did for the adits in the initial shafts, and then that's finally lined with concrete to create that cross passage. Within those cross passages, and that's from inside a cross passage, we do a final Mech Elect fit out. You can see a number of pumps. This would be a number of fire pumps and sump pumps for any water that gets into the tunnel, and also the electrical cabinets on the right-hand side, power, lighting, signalling, telecommunications. There's quite a lot that needs to go into the tunnel for the final rail operations. So the cross passages are very good for housing all that equipment. So as you go through a tunnel, you don't see all this. This is behind the door in the cross passage, but that's part of what our final Mech Elect fit out. So we're nearly done. Finally, the last bit of fitting out the tunnel is to put the rail and the rail systems through. So this is an image from one of the Singapore tunnels, and you can see there we lay the final track form through the tunnel, in the base of the tunnel, fit the final rail with the fixings and everything, and then on the wall you've got all the cables for your telecommunications signalling and firewater pump as well next to that cross passage. So that's the final fit out of the tunnel, and once that's done, we're ready to do final testing, commissioning, and hopefully run trains. So we've used a little bit of our BIM model there. When we get to the back end of this project in 2023-24, we'll go through a process of testing, commissioning, trial train running. We'll do some fire tests to make sure that all the systems and the ventilation are all working fine. And that'll be the completion of the tunnelling on the Cross River Rail project. So we've still got a long way to go. We've only just started, as you saw, some of those current photos of the progress we've made. 2021 is going to be a really big year for us. That's going to be our main tunnelling year. We're going to have the TBMs operating. We're going to have 5 road headers operating across 3 sites, excavating out the caverns and the tunnels. And encourage you to come on down to our Experience Centre at 151A Elizabeth Street, and you can see all of some of what I've presented. We've got cutter heads from the TBM. We've got a static model here behind me that you can get a feel for the alignment and learn a lot more about tunnelling, precincts, and what's happening on Cross River Rail. So that's all from me today. I hope you've enjoyed the introduction to tunnelling on Cross River Rail, and thank you very much for your time and attendance, and enjoy National Science Week. Bye for now.